No nation which expects to be the leader of other nations can expect to stay behind in this race for space.
Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to like and subscribe, and thank you for your support on Patreon. We appreciate you. Not long ago, a deep learning neural net system was asked a question. Can you improve on current energy reactor designs? Its answer was surprisingly brilliant. But to understand why, we need some basics. Nuclear fission power systems generate electricity by harnessing the heat produced from the splitting of atomic nuclei. This process is initiated by introducing a neutron into the nucleus of a heavy element, typically uranium-235 or plutonium-239. The unstable nucleus splits into two smaller nuclei, releasing a considerable amount of energy in the form of heat and additional neutrons. These neutrons can then initiate further fissions, resulting in a self-sustaining chain reaction. In a nuclear power plant, the heat from the fission reaction is usually used to produce steam, which drives a turbine connected to a generator to create electricity. However, the fission process produces radioactive waste, necessitating careful management and disposal methods to protect human health and the environment. When a fission reactor is initially started, an external neutron source is required to initiate the fission process. This is because the fuel, while it can sustain a chain reaction once started, doesn't have enough free neutrons to start the reaction independently. At this point, an important distinction should be made between radioisotope thermoelectric generators and nuclear reactors. RTGs are a type of nuclear battery that generates electricity through the natural radioactive decay of a radioisotope, typically plutonium-238. This decay process generates heat, which is then converted into electricity, usually using thermocouples, but some designs use Stirling engines, and the recent development of infrared photovoltaics should make these systems much more efficient soon. RTGs are simple, reliable, and can operate for many years, which makes them ideal for space probes, like the Voyager and Cassini spacecraft, as well as the large rovers that have been sent to Mars. RTGs work best for applications where refueling or maintenance is not possible. However, RTGs produce only a small amount of power for their mass. Nuclear reactors, on the other hand, utilize a controlled nuclear chain reaction that can be adjusted to generate heat, which can then be used to produce a large amount of power. This makes reactors more suitable for large-scale power generation, but they are also more complex. Most of these are thermal neutron reactors. This means that the neutrons must be slowed from high speed to low speed, also called thermal, for them to be absorbed by the target isotope. Light water reactors are the most common type of thermal neutron reactor. They are called light water because they use the most common isotope of hydrogen in the water, which is just a single proton, often called protium. Remember that hydrogen can also come as deuterium, which is one proton and one neutron, and tritium, which is one proton and two neutrons, and is radioactive. Light water reactors come in two main types, pressurized water reactors and boiling water reactors. In both types, water serves as both the coolant and the neutron moderator that slows down the neutrons, so that they are more likely to be absorbed by a nucleus and cause fission. In a pressurized water reactor, the reactor core is filled with fuel rods made up of pellets of usually uranium dioxide. These fuel rods are submerged in water. The water acts as a neutron moderator, slowing down the fast neutrons to make them more likely to cause further fission. The water also cools the fuel rods, carrying away the heat produced by the fission reactions. There are also control rods that are used to speed up or slow down the reactor. Control rods are made of materials that absorb neutrons, like boron or cadmium. By raising and lowering the control rods, operators can control the rate of the nuclear reaction. In a pressurized water reactor, the water in the reactor is kept under very high pressure, which prevents it from boiling. This pressurized water is heated by the nuclear reactions in the reactor core, and it carries the heat to a steam generator. In the steam generator, the pressurized hot water flows through thousands of tubes. On the other side of these tubes, there's a secondary loop of water at a lower pressure, which turns into steam upon absorbing the heat from the primary loop. The steam is then used to drive a turbine, which is connected to an electric generator. After passing through the turbine, the steam is condensed back into water and returned to the steam generator to be heated again. The giant towers you see at nuclear reactors are the cooling towers. It's their job to allow heat to radiate into the air and condense the steam back into water. The other common type of nuclear reactor is a boiling water reactor. Just like in a PWR, the BWR reactor core is filled with fuel rods and water is used as a neutron moderator and also a coolant, but with a key difference. Instead of having separate primary and secondary water loops, a BWR has a single loop where the water is allowed to boil directly in the reactor core. This boiling water produces steam which is directly piped to the turbine. After passing through the turbine, the steam is condensed back into water and then returned to the reactor core to be heated and turned into steam again, just like a pressurized water reactor. Both types of light water reactors have numerous safety systems, designed to shut down the nuclear reaction if conditions become unsafe, and to cool the reactor core, even in the absence of external power supply. They also have a containment shell to contain radioactive materials in case of a reactor breach. There is also a type of heavy water reactor, such as the CANDU reactor, which stands for the Canada Deuterium Uranium Reactor. The CANDU reactor uses the heavier but still stable isotope of hydrogen, deuterium, in its water to use as its moderator and coolant. This type of water is sometimes called deuterium oxide. The deuterium in heavy water is less likely to absorb neutrons than the simple hydrogen, also called protium, in light water. This makes deuterium a better neutron moderator. CANDU reactors have the ability to be refueled while operating, unlike light water reactors which need to be shut down for refueling. CANDU reactors are in use in several countries, including Canada, Argentina, South Korea, Romania, China, and India. The benefit to using heavy water is that since deuterium is a better neutron moderator than protium, and it can sustain a chain reaction with a lower concentration of uranium-235 in the fuel, this type of reactor can in fact use natural uranium as fuel, instead of enriched uranium, making the purchasing of fuel much less expensive. In a light water reactor, the uranium is enriched so that it contains about 3 to 5% uranium-235. Uranium-235 can be used to make bombs, which is why the enrichment level is limited. The rest is uranium-238, which decays much more slowly than 235. The half-life of uranium-238 is roughly the age of the Earth, 4.5 billion years. The half-life of uranium-235 is much shorter, about 704 million years. When a neutron from a decaying uranium-235 or other source strikes uranium-238, the neutron can be absorbed, turning the atom into uranium-239. Uranium-239 has a half-life of 23 minutes. At that point, on average, 50% of the uranium-239 will decay by turning a neutron into a proton, giving off an electron in a process called beta decay. This changes the number of protons, which changes the element, and we now have neptunium-239. Neptunium-239 has a half-life of about 2.35 days, after which half of it will have gone through another beta decay, becoming plutonium-239. And in the high neutron environment of a modern reactor, a significant fraction of the uranium-238 will be converted into plutonium-239. Plutonium-239 has a half-life of about 24,000 years, and it has many uses. In many commercial nuclear power reactors, a significant amount of the energy comes from the fission of plutonium-239, which is produced in the reactor from the uranium-238. Plutonium-239 is one of the materials that can be used to make the core of a nuclear weapon, due to its ability to undergo a rapid fission chain reaction. If you'll remember, the first atomic bomb used during war against Hiroshima was a uranium bomb, but the second one, called Fat Man, was a plutonium bomb. Now, plutonium-238, not plutonium-239, is used in RTGs for space probes and other remote equipment. And it's worth noting this because although they're isotopes of the same element, they have quite different properties. Plutonium-238 generates heat as it decays, which can be converted to electricity, while plutonium-239 is more useful for its ability to sustain a chain reaction. and is used, as we said, in modern atomic bombs and reactors. As explained in this lesson, plutonium-239 can also be used as a fuel in certain types of research reactors. And neutron irradiation of plutonium-239 can be used to produce other isotopes for medical and industrial uses. Most nuclear reactors are far too large to be useful in space. It takes about 250 tons of uranium and plutonium nuclear fuel to produce 1 gigawatt of electrical power in these reactors. And they can suffer terrible meltdowns if the cooling systems fail and the control rods can no longer be inserted, like happened in Chernobyl and Fukushima. This releases huge amounts of radioactive elements into the atmosphere. Reactors can be made smaller and safer, and many companies are working on this right now. In fact, nuclear reactors have already flown in space, discussed in more detail in this lesson. But there is a type of nuclear fission reactor that uses liquid nuclear fuel, called molten salts. These can be designed with a simple failsafe that shuts them off if they overheat by simply making a melt plug at the base of the reactor tank. Since the fuel is a liquid, if it gets too hot it will melt this plug, and the liquid fuel drains away into harmless reservoirs. The United States actually built and tested some of these in the 1960s, and China has one operating today. These molten salt reactors can reach very high temperatures without producing high pressure, making them more inherently safe. Let's look at the most common fuel source for one of these. Thorium-based nuclear power exploits thorium-232 as a fertile material, not fissile. Thorium-232 is not good as a power source, but it is fertile, meaning it can be used to produce a fissile isotope. Unlike most other radioactive substances, thorium is easily available on every continent. Inside the reactor, thorium-232 absorbs a neutron to transform into thorium-233, which decays to protactinium-233, and then further decays to uranium-233, which is a fissile isotope, meaning it can undergo nuclear fission, producing energy and additional neutrons. One promising design for a thorium reactor is the molten salt reactor. In an MSR, the fuel, such as thorium or uranium, is dissolved in a mixture of lithium and beryllium, which acts as both the fuel and the coolant. Here are the steps involved in a thorium MSR. Start with your fuel of liquid lithium, beryllium, and thorium-232. Then introduce neutrons into the reactor, either from an external source or from fission reactions within the fuel. Again, when thorium-232 and the fuel salt absorbs a neutron, it transforms into thorium-233, which decays into protactinium-233, which then further decays into uranium-233 over the course of about a month. The uranium-233 undergoes fission when it absorbs a neutron, releasing energy and more neutrons, which can then sustain the chain reaction. The heat produced by the fission reactions is transferred to a secondary coolant loop, which drives a turbine connected to an electrical generator. One of the problems with starting up any of the reactors is finding a startup neutron source. Californium-252 is often used for this purpose in many reactors, as it undergoes spontaneous fission and produces high neutron emissions. We said that a typical solid fuel reactor needs about 250 tons of enriched uranium to make 1 gigawatt of electricity, generating nuclear waste that must be stored for 100,000 years before it becomes safe. A typical molten salt reactor, on the other hand, only needs 1 ton of fuel to generate the same amount of power, and its radioactive waste becomes safe after only 300 years. But keep in mind, thorium reactors also need a neutron source jumpstart, just like uranium reactors. Now let's talk for a moment about fusion. Many nations are working on fusion power. Fusion power is a form of energy generation that attempts to replicate the process that powers the sun and other stars. In nuclear fusion, light atomic nuclei combine to form heavier nuclei, a process that releases vast amounts of energy. The most commonly studied fusion reactions involve the isotopes of hydrogen, deuterium, and tritium. However, fusion reactions require extremely high temperatures and pressures to overcome the electrostatic repulsion between atomic nuclei. This has posed significant technical challenges, and despite decades of research, no practical fusion power system has yet been developed. If these challenges can be overcome, fusion power has the potential to provide a near-limitless clean source of energy, as the fuel, in the form of deuterium, is abundant, and the process produces minimal radioactive waste. The problem is not how to get elements to undergo fusion. We've been able to do that since 1932. when Ernest Walton used protons from an accelerator to split lithium into alpha particles, which are just helium nuclei. The problem is getting more power out than we put in. We all celebrated when the National Ignition Facility delivered 2.05 megajoules to a deuterium target and produced 3.15 megajoules of fusion energy. The problem is it took hundreds of times more power to deliver the 2.05 megajoules. And while some fusion reactions are aneutronic, meaning they don't produce neutron radiation, discussed in this lesson, the most abundant fuels that can most easily be used do produce neutron radiation, and a lot of it. There are a lot of reactor designs out there. Most of them were invented between 1950 and 1970. From the simplest magnetic mirrors and inertial electrostatic confinement fusion devices, so easy to build that a 12-year-old in Tennessee made a working fusion reactor at his home in 2018.
I have been able to use electricity to accelerate two atoms of deuterium together so that they fuse into an atom of helium-3 and also release a neutron, which can be used to heat up water and turn a steam engine, which in turn produces electricity. So I'm going to be demonstrating what's called a demo run, so I won't be doing full-on fusion, but I'll still be creating a plasma within the chamber here. And the first step to doing that is turning on this pump here, which will remove most of the air, and that takes about 10 to 15 minutes for it to do its job completely. I've been working on this project for about 2 years and about 1.5 years to originally achieve fusion. This project was very complicated. I'd say the hardest part was figuring out how to make the seal airtight on the chamber. So I spent about probably half a year trying to get the seal correct so that it wouldn't leak out air. So once this pump has done its job, then I turn on this pump back here. This is called a turbomolecular pump. What the turbomolecular pump does is it removes the last tiny bit of air needed to be removed so that fusion can occur. It spins up to 10 times faster than a jet turbine does. There are definitely some parts of my project where my parents were definitely questioning whether or not they should keep giving me funding to do this.
There were a few moments during the project that I had some reservations. I would definitely be Googling things before he turned on various stages.
You know, I didn't know enough, just like his mom. We didn't know enough to have reservations, to be honest.
He did a great job of explaining it to us and all the precautions and why it was safe, and so I ultimately ended up trusting him.
Once that air has been removed, I add back a tiny bit of gas in the form of deuterium. Deuterium is an isotope of hydrogen. An isotope means a type, so it's just a different variation of hydrogen. All right, so now the pump has removed most of the air from the chamber, and I'm going to go ahead and turn on the electricity to create a plasma. So as you can see, a plasma that looks like a glowing ball of light has been created inside of the chamber. And if I were going on a fusion run, so I was actually attempting fusion, I would now add some of the deuterium gas, which is the fuel. I achieved this record when I was 12 years old. So as a young child, like most kids in my school, we all loved the Guinness World Records books at our school library, so we would all go down there and check them out every day. It feels great to be a Guinness World Records title holder.
This IECF is also sometimes called a Farnsworth-Hirsch fuser, or simply a fuser. Then we have the Z and theta pinch designs, which use powerful electric currents through a plasma to create self-generated intense magnetic fields that compress the plasma to fusion conditions. These are easiest to build if you want one at home, but too unstable, so far, to generate surplus power. Then we have stellarators and tokamaks, which are either a twisted or straight torus, around which magnetic fields confine and compress plasma, while radio waves are pumped in to heat it. The Wendelstein 7X in Germany is the most advanced stellarator in operation, and the ITER reactor in France is the largest tokamak. Though my money is on the much smaller Spark reactor, designed at MIT and discussed in depth in this lesson. Next we have inertial confinement fusion, like the National Ignition Facility, where powerful lasers compress a deuterium fuel pellet. Then we have the field-reversed configuration and the spheral mock. Both of these use a toroidal plasma with a self-generated magnetic field. Many of these fusion reactor designs seem promising, and there are many others out there, but when built at a large scale, they all have problems stabilizing the fusing plasma. Most of the spheral mock and FRC research was phased out by the early 2000s. But another fusion reactor design that I think shows promise is the Helion energy design, discussed at length in this lesson. In brief, the Helion reactor is a combination inertial confinement fusion and magnetic confinement fusion called magnetoinertial fusion, or MIF. This is also a type of field reverse configuration reactor, which gets really confusing. Let's look at how it works. Plasma formation. Deuterium fuel is ionized to form plasma at each end of the device. Field reversal. Electric currents are run through the plasma to create a self-contained magnetic field within the plasma itself, which is a toroidal or donut shape, like a smoke ring, hotter than the surface of the sun. This field reverse plasma confines itself, so there's less reliance on external magnetic fields for confinement, which has been a problem in other types of magnetic confinement fusion like tokamaks. Plasma collision and compression. Two of these self-contained field-reversed plasmas are then shot towards each other into a central chamber. When they collide, they merge, which causes a significant increase in temperature and pressure. Pulse magnetic field compression. The merged plasma is further heated and compressed using a pulsed magnetic field. If the temperature and pressure are high enough, fusion reactions occur. Direct energy conversion. The fusion produces high-energy helium nuclei, also called alpha particles, and neutrons. The alpha particles are confined by the magnetic field, and their kinetic energy is converted into electricity directly. No need for water or steam or turbines. The neutrons, which are not confined by the magnetic field, can be used to breed very valuable isotopes through reactions with a lithium blanket surrounding the fusion chamber. This lithium blanket is part of a tritium breeding concept. Tritium, after protium and deuterium, is again the heaviest isotope of hydrogen, and it's also radioactive. It is very rare and very expensive. When a neutron strikes a lithium atom, either the most common isotope lithium-7 or the less common lithium-6, a fusion reaction creates an alpha particle, also known as a helium-4 nucleus, and tritium. This tritium is very valuable, as the tritium-deuterium fusion reaction is the easiest to achieve. While the Helion machine uses the much more difficult deuterium-deuterium reaction, many other reactors, like the massive ITER, will need tritium to work. Tritium is also needed for atomic bombs, so if you want to buy any, you are competing with the U.S. military, which routinely pays up to $1,420,000 per kilogram for it. Tritium has a half-life of 12 years, meaning it decays at a rate of about 5.5% per year. This whole process is repeated several times per second in a pulsed manner in the Helion reactor. The ultimate goal of Helion energy is to develop a reactor design that can sustain these reactions long enough to achieve net power production. The ability of the Helion reactor to produce tritium from abundant lithium and deuterium could make it a very cost-effective design, even if it was not an excellent power reactor. But let's look at the most recent progress at Helion Energy. Back in May of 2022, Helion completed their largest ever pulsed power test. This test was named Vela after the Vela pulsar and was designed to demonstrate new advanced switching and capacitor technology. This demonstration pulsed the reactor once every second, or 1 Hz, producing 11 gigajoules of energy. Like many successful technology companies, Helion has discovered that if it wants the best components possible, it will need to build them itself, and Helion is now manufacturing its own capacitors and control systems. To complete a project named Polaris. Polaris will be the world's first commercial fusion reactor when it comes online, and is scheduled to start power production in 2028, providing power to their first customer, Microsoft. Commercially viable fusion energy will be an amazing advancement for human civilization. And what else could this awesome reactor be used for? You may notice that if you cut one of these reactors in half, it would make a nice fusion drive for your spaceship. In fact, the Helion reactor did not start as a fusion power system. It started as a fusion propulsion system, designed by NASA long ago for deep space missions. When funding was pulled from the NASA project, the scientists decided to point 2 fusion drives at each other and make a power generator. But what does all this have to do with an AI looking at better ways for humans to make power? The AI pointed out what seems an obvious concept, and I'm sure others have thought of it before. Why not put a neutron-generating fusion reactor, like the Helion energy design, inside the core of a liquid thorium fission reactor, insulated by vacuum and cooled from the heat, of course? When you start your fusion reactor, using cheap and abundant deuterium as fuel, it will produce a flood of neutrons. These neutrons will then start the thorium chain reaction, creating a controlled, highly efficient fission reactor. Shutting off the fusion reactor shuts off the flow of neutrons. If 1 ton of thorium fuel can produce 1 gigawatt of electrical energy, we can feed some of that back into our battery packs used for startup, and we can use some to strengthen our fusion reaction. The excess could go here to power these fusion propulsion systems and the rest of the ship. We could have a compact, extremely powerful, controllable and safe hybrid fusion-fission power source. And finally, have a fusion-propelled spaceship. A deuterium fusion rocket would have a specific impulse of up to 130,000 seconds. Compare that to the best chemical rocket engine at 465 seconds, and the estimated performance of a nuclear thermal rocket at around 900 seconds. A specific impulse of 130,000 seconds gives us an exhaust velocity of 13,252 meters per second. Putting that into the rocket equation tells us that we could launch a single-stage Starship only from Earth, fly to the moon with 180 metric tons of supplies, equipment, and crew, spend months exploring and setting up remote mining operations, then come back and land, all without refueling. In fact, a fusion-fission rocket system could provide the high thrust and high specific impulse needed to open up the entire solar system. Something to think about. Thanks for listening, and stay safe. At Astra Pro Terra.
I'm Dr. David Kirtley of Helion Energy. I want to start and thank my co-authors, Brian Campbell, Andrew Hine, Richard Milroy, Chris Peel, Rachel Ryan, and George Vatrabek, and the rest of the Helion team. This work today, we're going to be talking about our 6th fusion prototype called Trenta, which is a pulsed magneto-inertial fusion compression prototype. Specifically, we'll be discussing the vacuum vessel, diverter design, and then results of 16 months of operation in 2020. So today we'll briefly talk about the advantages of pulsed non-ignition magneto-inertial fusion, dig in a little deeper to field reverse configuration plasmas, an overview of the Trenta program itself, and then a deeper dive into the diverter, the materials, the magnetic topology, vacuum system design, and then some wear analysis and conclusions of this work and discussion of ongoing next steps. So our approach to fusion uses pulsed non-ignition MIF, where we take a field reverse configuration and then compress it to high temperatures, to thermonuclear conditions. Some of the key benefits here that are unique among fusion, the material boundary, the magnetic radius, is significantly larger than the gyro orbits at all times. So we have complete vacuum boundaries, so no plasma material interface during the high temperature compression. Diverter is a different story, we'll get to that. With pulsed magnetic compression, we've been able to show that you can do adiabatic compression to high temperatures at very high efficiencies, leading to lower gain requirements for fusion. Pulsed magnetic systems are fundamentally non-destructive, with theoretical repetition rates much greater than 1 hertz, allowing you to minimize the scale of the system, therefore build systems faster and lower capital requirements and get to fusion sooner. And then most importantly, an inductive compression scheme, especially pulsed inductive compression, allows direct energy conversion. through just MHD conversion. And we've been able to show that you can, in fact, do this through a compression and expansion cycle that extracts particle energy directly. However, some of the key challenges, while direct energy recovery allows you to use alternate fuels, those have increased ion temperature requirements and equilibration requirements, both of which need to be satisfied. We've showed confinement now well over 5 keV temperatures, and that our scaling, even dating back to the large S experiment program, holds. However, we have to continue to demonstrate that beyond 10 keV and higher. That remains to be done. First wall design, fundamental to these system designs is the limit of the first wall. We want solid first walls in all FRC systems, and what that fundamentally means is a power loading of X-ray and neutron radiation of less than 10 megawatts per square meter. However, even that, for those who study the field, know that that's a really tough and demanding requirement that we're pushing boundaries on. We'll talk about that today too. And then pulse magnets in a neutron environment require replacement. And so that replacement cycle and the economics of that and the mechanics of that are work to be done. Finally, diverter. At the exit of one of these pulse cycles that we'll talk about, the remaining plasma does expand, translate into a diverter, in which case we actually need to cool it, expand it, and deal with it. So like all fusion diverters, tokamak or otherwise, and MFE and MIF and MTF systems, the material science challenges, the magnetic design is actually a large challenge. So that's the main focus of this work today. So a quick overview on field reverse configurations. So for those of you not familiar with an FRC, this configuration of plasma has been studied extensively. An FRC shown here is a cylindrical magnetic topology. Fundamentally, they're closed field, self-organized, compact toroids. What that ends up being for an FRC, which is a high pressure device, is beta very close to 1, the average beta condition of an FRC. And so that allows you to do a couple of really key things. One, you know, at any time from an external magnetic field measurement, you know the internal plasma pressure, and you can know the internal plasma profile. That's pretty critical. FRC profiles, unlike most fusion plasmas, are uniform or close to uniform, and have been studied extensively. Pressure balance, because beta is near 1. You always have for an external magnetic field measurement as well as an applied field, you know with high certainty what the internal density and total temperature are. This becomes a pretty critical diagnostic for us. You'll see this throughout, where external magnetic field measurements and magnetic flux measurements allow us to know, and interferometry measurements allow us to know temperature, total temperature. Measuring ion and electron temperature separately requires separate diagnostics that we'll talk about. And finally, this is the most important. The average beta relationship gives us an axial pressure balance as well. We can talk, I would direct you to literature for that, but that shows us very clearly the relationship of the length to the radius as well for any external compression field. So this then allows us to design a complete system from first principles that will get to full thermonuclear conditions using an FRC. So some of the key relationships are shown here on fundamental FRC scaling relationships. So shown are the energy confinement times and particle confinement times. This is derivations of lower hybrid drift, R squared over rho I scaling. But what that has enabled us to do now is, with empirical relationships built up over a history of programs by us and others, put together pretty well-defined, called the LSX scaling, and then the modified LSX scaling. And we'll show today how at higher temperature we've been able to extend that, but shown some deviations from that as well. Also critical for amount of trapped colloidal flux, you have a given amount of external field and radius for a given compressed plasma. Using these relationships and adiabatic compression, you can see on the right here are final compression relationships. So for a given magnetic field, an initial magnetic field and then a peak compression magnetic field, we can then a priori design a system for ion electron temperatures as well as densities required to get to fusion conditions. The other key requirement for field reverse configurations is stability. Fundamentally, FRCs are MHD unstable to the tilt instability. This is a major instability that should drive total confinement of these systems. It has been shown by us, others, as well as others, and starting with the large S experiments program reference is shown here, that FRC tilt instability is stabilized to an extent by the kinetic motion of the ions within the plasma itself. Kinetic stability as well as Hall stability have both been theorized, and then we have an empirical scaling that's well proven over a number of experiments that show that as long as you are at an S star over E, which is a ratio of the ion gyro radius to the elongation of the plasma of less than 5, that these systems are in total stabilized against the tilt stability. This enables us to build systems that have a theoretical stability limit in MHD stability in the microseconds or nanosecond level, but actually extend them to hundreds of microseconds or milliseconds. This, in addition to the adiabatic scaling relationships, sets the whole parameter space of what we design a fusion system using FRC compression. The other key component to this is after an FRC is compressed, the two fusion conditions. In this case, we'll be talking about an excess of 8 keV total temperature and ion temperature. These plasmas, we have to actually expand them and exhaust them. And that's where some of the key physics and engineering of these systems comes into play. So we've designed these diverters on either axial end of our system to be able to handle up to 100 kilojoule plasmas per pulse, with expecting of ions in the 10 keV deuterium and helium ions, as well as a limited number of the pulse fusion products. So this is MEV alphas, protons, deuterons, and tritons. These end up being very critical design parameters, as you might imagine. The last real key requirement, and this has been studied by us as well as others, and there's some references attached, is electron thermal conduction. Like all fusion plasmas, electrons are the primary thermal loss mechanism, and in the diverter, we fundamentally have to try to minimize that while actually having materials that can take the plasma bombardment of both the low temperature plasma ions and, most importantly, the fusion products. So we designed these systems fundamentally to be below 10 megawatts per square meter is a key limit. We believe that's actually also really challenging to do. So we focus on systems that are 5 megawatts per square meter and lower. And then the approach that we've taken here, we have several on the Trenta system. What we're describing today is a cylindrical cusp geometry. I think this is similar to a traditional X diverter topology, where here we actually, after a post-expansion, we compress, we have a mirror geometry to high field, then we cusp and expand that out to the walls. In this case, specifically, the data shown here is a dielectric wall, interestingly enough. The dielectric can still set up a sheath. That sheath will then limit thermal conduction to the wall. This was shown by others. We've been able to show this now at scale at thermonuclear conditions. The other part to this is in the diverter. This work has been looked at extensively by others, somewhat in our research staff as well, or some of the pioneers here. But you can actually stabilize the FRC against its next most serious instability, which is an N=2 rotational instability. In all the data we're going to be showing here, there was no actual edge biasing or other stability mitigation. And so these plasmas were terminated not on a tilt instability timescale, but on a rotational instability growth. There is no addition of any kind of stabilizing system in what we're showing here today. Overview of the Trenta experimental program. What we did here, what we aimed to do, and then we're successfully able to do, is take two large-scale, 2-meter scale FRCs, accelerate 2 of those 2-meter scale FRCs towards each other to a central compression region, merge them at supersonic compression and merging, references are attached, and then compress those to high temperature. Here well over 5 keV total temperature. The goal of this program is to get even hotter than that. As well as keep diverter loads on those pulse systems less than 5 kilojoules per meter squared. So expand those plasmas to large-scale diverters that you can see here in these pictures. We're not going to dig in too deep into diagnostics. There's a whole host of plasma diagnostics on this system, ranging from magnetic interferometer, infrared interferometers, Bremsstrahlung radiation, X-ray spectrometers, and a whole host, as you can see here, of neutron diagnostics. We're going to touch just on the operation of this system. This is data through the end of 2020 from operating from as low as 3 Tesla compression all the way up to above 7 Tesla compression. Again, this is our Mark I diverter, so that is a cylindrical cusp geometry. All the lifetime of these plasmas are limited by the onset of the N=2 rotation. And then, most importantly, little to zero observance of any destructive tilt. You can see in the bottom left here the scaling relationships of expected confinement lifetime, and this is particle lifetime and magnetic flux lifetime. You have to be a little bit careful here. Magnetic flux is not energy explicitly, but generally we consider them relatively close to each other for these high beta plasmas. And so the relationship shown here is from Alan Hoffman and the LSX team, and then extended beyond that in their follow-on programs. And what you can see here is then a comparison of our measured flux lifetimes. We also have particle lifetimes, but here I'm showing the flux lifetimes of the Trenta system. These results, we showed that lifetimes at low temperatures that were on the LSX timescale within error bars, but interestingly enough, as we went to higher temperatures and lower densities, those relationships, we actually exceeded the LSX types lifetime flux and energy confinement times by over a factor of 4. And you can see the data here of that increasing trend as we increase in total plasma temperature, in the data shown here up to over 8,500 electron volts of total plasma temperature. The other interesting thing that FRCs have that are unique is because you have a pulse systems where the ion and electron equilibration times, the operation of the machine is less than the ion electron equilibration time. You can actually have an ion and electron temperature gradient within this system. And this we were able to observe here actually more than any system previous, where typical systems have shown from 0 to maybe 5 times a ratio of ions to electrons. Here we exceeded 10 times the ions to the electrons, with electrons in some of these systems well exceeding 1 keV electron temperature and ions exceeding 8 keV ion temperature. And these are not these are emerged, compressed, a static system. We're not talking about emerging or any kind of collisional temperature situation that you may have in other merging or particle beam type systems. Error bars here represented in terms of understanding of the magnetic topology as well as calibration of those X-ray diagnostics for the electron temperature. So getting to some of the key engineering requirements of these systems, these are a little bit different than other plasma systems. We talk about a sweet spot in between magnetic fusion systems and traditional inertial fusion systems with pre-compressed neutral densities in the 1 to 100 millitorr territory. That's obviously at room temperature gas, and then compressed plasma densities and the low, say, few Tesla systems, 10 to the 21, all the way up to 10 to the 24 peak compression densities. And what that means is because our neutral density is in the millitorr and tens of millitorr territory, our background pressures can be actually quite a bit higher before impurities start to have an issue. We don't see impurity-driven losses for electron temperature, for instance, all the way up to the 10 to the minus 4 territory of torr background gas. And so a lot of the impurities and leak rate things we can ignore, which means we get to move to elastomer seals. However, elastomer seals obviously in a high temperature plasma environment have a lot of challenges. So what we've been able to show here is we can build systems that have a quartz shadow shield interface on every elastomer, high temperature gasket, and then we differentially pump the backside of those gaskets to prevent, again, further leaks or any kind of interaction with any outside leakage. And then finally, by building these systems as robustly as they were, we are able to actually pump down these systems with a number of these seals and then stay under vacuum for 16 months straight and do several thousand, almost up to 10,000 operations of this system. The last thing I want to say is that not all of our gaskets have this, but everywhere we can, we add electromagnetic shield, but essentially have an axial magnetic field that means that any low temperature electrons that are magnetized, that actually escape, that are getting near the wall, we can actually keep those out of those gaskets. In previous systems, we have seen ion and plasma bombardment of seals and have seen contamination from them. In this machine, we watched with the monochrometers on the previous slide and didn't see any actually impurity-driven cooling or radiation losses from these seals. The diverter itself, there's a lot of key requirements in these systems because we have some pulsed magnetic fields. We have to use a lot more dielectric materials than people are used to. So here we're showing a cylindrical silica geometry and then an end geometry of usually a high Z. Early experimental work used just stainless, but then we moved to high Z molybdenum and have looked at tungsten as well on those systems. Again, the key here is a cusp design. And a magnetic cusp you can see here, which is an MHD, a hybrid PIC code, where we have an MHD simulation overlaid with particles that are tracked within that MHD fluid simulation. And we watch the low temperature plasma as it evolves and bombards the wall as it expands and cools. However, the high temperature, particularly the fusion products, are not confined by that cusp, and they expand and hit the wall. And so in this system, we're observing this, we're looking at the damage, we're measuring through probes what that damage was of this system. And what that enabled us to do is look at the evolution of these materials. So this high energy pulse, 5 kilojoules per meter squared, still does ablate some material. So we have quartz that's ablated from windows as well as from the dielectric material, and then redeposits. And so we're able to measure that ablation and measure that redeposition over time. For the operation of tens of thousands of pulses, this wasn't a problem. But what we imagine is that actually over millions and billions of operations that we need to address this. So in conclusion, our 6 prototype Trenta demonstrated that we can build repeatable, sustainable, greater than 5 keV plasmas and operate in a cylindrical cusp diverter. So far, that diverter cusp design, even with a diamagnetic boundary, it's provided sufficient thermal conduction and mitigation of any losses for the low temperature plasma. Quartz erosion and the silica erosion is ongoing but minor, and would be a life limiter for a long-term operation of one of these systems. Future work is going to require higher field magnetic shielding, which we're implementing right now, and with a focus on getting lifetime and, more importantly, handling the MEV fusion products. So I want to thank the funders for this work. This work was primarily funded through private investors, Mithril Capital, Capricorn, and others. And we look forward to telling you more about the work being done on Trenta in the future.